Hi, I'm Mr. V. This is Illustrative Mathematics, Unit 5, Solid Geometry, and we're on Lesson 4, which is Scaling and Area. I'm doing this lesson for those of you who missed the lesson for whatever reason, or who want to review what it was that we talked about in class. And in this lesson, the goal, the objective is to say, I know that when figures are dilated by a scale factor of k, their areas are multiplied by k squared. Normally, I would have you explore this and then rehearse this at the end. I'm going to talk to you explicitly to begin with, though, on what it is that we're going to be learning and exploring today. So here I have a point of dilation. At the point, this has no dimension. This has no length, no width. This is the point of dilation where k is equal to 0. This is my center of dilation, if you want to think of it that way. If my original figure is this blue one, this would be where the k, or the scale factor, is 1. This is where we're going to have congruence and congruent figure. So if I scaled something by 1, it would be congruent to my original. If my scale factor is between 0 and 1, it has to be larger than this point, but it can be smaller than this one here. This would be getting smaller. And if I have a scale factor that is larger than 1, it would be getting larger. We start at the point of dilation. If I go the distance from the point of dilation to my original, that is 1. So if I'm going to go smaller, it would be shorter distance. If I go double, say for instance, I would go this distance and I would go that distance again to get this far. You do that for each of the vertices to go from the point of dilation. Now we know from previous that if I take my original length, say this length right here, length 1, and I multiply it by some scale factor, it's going to get me to my new length. So if this scale factor is, say, 1/2, then this would be 1/2 of whatever that was. If it was double, it would be double that length. In today's lesson, what we're learning is that the area, in order to get to the new area, we have to multiply it by not by the scale factor k, but by k squared. This is the big idea. And in a future lesson, we'll learn that volume is going to be by k cubed. This has a length component and a width component. The length is scaled up by k, and the width is scaled up by k. And we'll discover that as we go through the lesson. So the first thing we asked was, what number times itself is equal to 25? What number times itself is equal to 81? What number times itself is equal to 10? Most of you would say that 5 times 5 is 25 and 9 times 9 is 81. I get an assortment of answers for the 10, though. And the reason is because 10 is not a perfect square. So another word for multiplying a number by itself is called squaring the number. We represent this with an exponent of 2. So you have a base and you have the exponent. You multiply the base by itself that many times. You do not multiply the base times the exponent. You multiply the base by itself, the exponent number of times. So 5 times 5 is 25. 5 squared is 25. And we can take this process backwards, and the inverse of squaring is taking a square root. So the square root of 25 is 5. And the number of 25 is called a perfect square because its square root is a whole number. Now let's look at some perfect squares. So perfect squares, these are numbers that you should know, and you probably do know, but you might have done this in an earlier grades. In fact, you start learning multiplication in 4th grade, and I think you might know your perfect squares certainly by the time you're in 6th grade. So we have 4, 6, 9, 16, 25, 36, 49, 81, 100, 64, 81, 100. And that's good. If you've memorized these before, that shows that you know how to memorize, and you should memorize them up to 25 by the time that you're in 10th grade anyway. 25 is 625. 15 squared is 225. And any of these other ones, 169, 19 times 19 is 361, 24 times 24 is 576, and so forth. And this is so that you can recognize patterns, because patterns will get bigger as you go. Maybe if you're a swimmer or something, or a cross-country runner, and you want to occupy your mind as you're going, just repeat 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, or something like that, and do it up to 25. The next activity that so 10 is not a perfect square. You notice that 10 doesn't fall in here. 9 is a perfect square, but 10 is somewhere in between. So when we do 10 squared, what number times itself is equal to 10? That would be the square root of 10. This is the exact number. It's about 3.2, but the square root of 10 is even better. When you multiply the square root of 10 times the square root of 10, you get the square root of 10 times 10, which is the square root of 100, which is 10. So what number times itself is equal to 10? The square root of 10. When you multiply a radical by itself, it's equal to the radicand. That's the thing that's underneath the radical sign, radicand. Our next activity is to look at these next few pages. First, we have, and I'd like you to try these on your own. You can watch part of my video if you want, and then pause it while you try the rest of them. There's a rectangle. We're going to find the area of the rectangle. We're going to scale this rectangle up by a scale factor of 3 and then calculate its area. Then we're going to fill in this table, scale up that original rectangle by all of these different values, and then determine by what value the area changed. So, for example, here we have a rectangle. And the area of a rectangle, the formula is area is equal to length times width. My length here is 2, my width is 5, or 5 and 2, and my area is going to be 10 units squared. And I can put these numbers in a table. I'll put them in this table. So 2 times 5, that's 10. And the scale factor I changed, it didn't change from my original. This is the congruent situation. Remember the congruent? You multiply it by a scale factor of 1, it's going to equal the same. What if we took this original and we scaled it up by a scale factor of, say, 3? When you scale it up, and this is important, pretty important, I suppose. If this is one part, I'm going to go 3 parts. There's 2, and there's 3. If I go this one 3 way, I'll go, there's 5, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So we're going to go over to here, and then I'll go up to this point. You could do it diagonally, or you just go straight up and down the vertical up to that point and straight across on the horizontal. And this is 15 by 6. So again, my area is equal to length times width. I have 15 times 6, which is equal to 90 units squared. And we put this number into our table. When the scale factor was 3, we got an area of 90. What factor did we have to multiply this original by to get to 90? Well, we multiplied it by 9. And at this point, I'm going to point out to you their scale factor, this is k, and the scale factor by which it changes each time it's going to be k squared. So this is 3. This would be 9 times larger. It's scaling both in the length by 3 and it's scaling in the width by 3. And you can see that on the drawing here. I had to scale the length by 3 and the width by 3. What if we did it by 4? So if I do 4, I have 1 part, 2 part, 3 parts, 4 parts. This is 8. I have 5, 10, 15, 20 comes out to here. And this is going to be 20 by 8. So my area, length times width, here's the area, is 20 times 8, which is 160. How many times larger than the original is this? How many of these originals does it take to fill in this? Well, it's going to take 16 of them. I'm scaling it by 4 in the x direction and scaling it by 4 in the y direction. So my number becomes 160, and this is 16 times larger. And you could do these others as well. This would be 440, so this would be a scale factor of 4. This would be 2.5, and it's a scale factor of 1/4, which is 1/2 times 1/2. And 2.5, this is 62.5, which is 6.25. And this number is nice because it comes into play with this one here. I have 25 squared. I have 2.5 squared. I have 2 decimal places, 6.25. So every time it works. And the next question said, well, what if you had a rectangle. What's the area of a rectangle? It's length times width. And then it said, what if the length of a 1 by 2, so if I have a 1 by 2, what if you were scaling this up by a scale factor of k? This would be 1 times k. This would be 2 times k. My area here is 2. My area here is going to be 2 times k times 1 times k, 2 times 1 times k, which is 2k squared. This goes up by a factor of k squared. What if instead of going up by having an original area of 2, what if it had an area of a? How long would it be if I were to scale it up by a scale factor of k? Well, this is going to be k more in this direction. It's going to be k more in this direction. So it's going to be a factor of whatever my original area was times k squared. And that's the big idea of what we have with our lesson today, is to show that the new area is not scaled by a factor of k. It's scaled by a factor of k squared. This is what we just talked about. You could do this for any shape. You could divide it into rectangles. You can make smaller and smaller rectangles, and then you could dilate each of those in the length and the width by a scale factor of k squared, and it works no matter what the shape is. Here's the last question that we have. Suppose you have a circle that has an area of 20. So I'll draw a circle, an area of 20, and it has a radius like this. I'm going to scale it up by 6. So I have 1, 2, 3, 4, 5, 6 in like the length direction or radius direction. And you scale it up. How many times larger is this new one? Well, my formula is my area times the scale factor squared is going to equal to my new area. We substitute the values with 20 times 6 squared. This is 36 times 20, which is 720 square units. That would be 36 times larger than the original. That's the way that you would do these problems. There is a summary page, lesson synthesis and a summary page. And then this last question, which is, if you have a 6 by 10 rectangle and it's dilated by a factor of 3, what's its new area going to be? I'll just show you this one. If I have a 6 by 10, I'm going to scale it up 3 this way, and I'm going to scale it up 3 this way. So there's two ways of looking at this. You could say, I could multiply 6 times 3 times 10 times 3. Or I could use this other formula, saying my area of my original times the scale factor squared is equal to the area. I'll choose to do it both ways, but I'll choose this way first. 6 times 10 is 60. I multiply that times 3 squared, which is 9, and I get 540. Similarly, if I scale up the 6 in this way by 3, I'm going to get 18, and scale up 10 by 3, I get 30. And when you multiply 30 times 10, you also get 540. And that's today's lesson. So good luck and success.